My invisible friends, hello and welcome back to our series on electrical engineering. First, apologies for the background noise. I am in a public place right now, but this video could not wait. This is the final video on my sub-series on the solution of the effect of having reactive elements in an electronic circuit. First, we have seen that as soon as we do that, the algebraic equations of the circuit become differential equations. As of late, we've learned to find the initial conditions and how to include those conditions in the solution. Let's work on this. First order system, the solution. We have seen that in RC and RL circuits that have only one reactive element, that is, they have either one inductor or one capacitor, the differential equation for any voltage or any current has this form. It is a first order ordinary differential equation. It is described by three constants, the coefficients A1 and A0, and the constant K on the right hand side. Let's focus on the solution. In math courses, we've learned that the solution of such an equation has an exponential function of time. Let's turn the page and refresh our memory on the exponential function of time. A function like that, y of t, could be a voltage or could be a current, in our case, a function of time. That function of time begins at an initial value y0 and eventually will get as close as we could imagine to a final value y of f. The amplitude of that exponential is y0 minus yf. At a certain point in time tau, the value left of that amplitude will be only 37% of the original value. That tau, that time constant, is an indication of how quickly that exponential reaches for the final value. Some systems have very small taus, they have very responsive. They go for the final value very quickly, others not so much. That is the expression of that exponential, right? It has the amplitude y0 minus yf of the exponential, the time constant tau, and the final value y of f. That is the solution to this differential equation. But the differential equation itself can give us more data about that final solution. Let's see. If we wait long enough, that exponential will be so close to the final value that for all engineering practical purposes, it will be the final value already. That happens for any t after 5 times tau. Check it out. At that point, the rest of that exponential would be less than 1% of the original amplitude, and the function of time will be very, very close to y of f. So we say, after that 5 taus, the function is already y of f. It is a constant. If it is a constant, then the derivative is 0, and the differential equation can be written just like this. From there, we solve for the final value, k over a0. In math courses, we've also learned that the time constant is given by the coefficients of the differential equation, a1 divided by a0. Those are the two formulas that we carry over from math courses into our solution. Let's explore the possibility that y0, the initial value, is given to us. The problem at hand is clear. For an RL or RC circuit, any voltage or any current is given by a first-order differential equation. Remember the tutorial that you saw before this video, right? In that circuit, the voltage in the capacitor was given by this differential equation, a first-order ordinary one. Let's expand the description of that problem. A capacitor that has an initial voltage of 10 volts is connected at t equals 0 to the circuit in this figure. What is the voltage of the capacitor as a function of time? We have seen that the differential equation that describes that voltage is this one. From there, we obtain the final value, 90 divided by 30. 3 volts is the final voltage in that capacitor, and the time constant, 1 over 30. A1 divided by A0. So, if the initial value is 10, we can write that the voltage in the capacitor is initial value 10 minus final value is 3, e to the negative 30t plus the final value 3. That is the voltage in that capacitor. But what if it's up to us to find the initial condition? In the previous video, we learned that in DC steady state, all voltages and all currents are constant, and as a consequence, in DC steady state, inductors behave like short circuits, and capacitors behave like open circuits. Let's take advantage of all that to find the initial conditions ourselves. I have chosen to explain that in a tutorial mode, so bear with me. This is often the case, that before t equals 0, the circuit was in DC steady state. Very often the case in first year courses in electrical engineering. It is worded differently, but it means the same. It's written with words like, the circuit has been like this for a long time. That means that the circuit is in steady state, and we look at the sources on their own DC. Bingo, we're in luck, we are in DC steady state. We determine the voltage in every capacitor right before t equals 0, still in DC steady state. And because the voltage in the capacitor will not change instantaneously, that is the voltage in the capacitor right after t equals 0 as well. It is the initial condition. It is VC0. The same can be said about currents in inductors. Let's go over a complete RC example. The switch in the circuit has been closed for a long time. At t equals 0, the switch opens. Right, the voltage in the capacitor as a function of time. Fine. The switch has been closed for a long time. The circuit was in steady state. The only one source is DC, it's DC steady state. Because the switch is closed like so, it is bypassing that 2 ohm resistor. So in reality, before t equals 0, that switch is bypassing that resistor and the circuit looks like that. But the circuit's been like that for a long time. It was in DC steady state, and the capacitor then was an open circuit. This was a snapshot of the circuit before t equals 0. Because the current in that branch is 0, the voltage drop in that 2 ohm resistor in series with the capacitor is 0, and the voltage in the capacitor is just the voltage of the node V1. But that voltage is given by a voltage divider of 9 over 2 and 2, 4.5 volts. Fine. That voltage at 0 minus right before we open the switch is going to be the same voltage in the capacitor after we open the switch, because voltages in capacitor cannot change instantaneously. That's going to be our initial voltage in the capacitor. Now, the switch operates, the circuit looks like that, but we already know the initial voltage in the capacitor, 4.5 volts. The differential equation we find as before in the previous video, that gives us the final value, the time constant, and we can write what is the voltage in the capacitor. Initial voltage 4.5, final voltage 3, the time constant 1 over 30. That is the voltage in that capacitor after we open the switch. Do you see a pattern here? You will take a snapshot of a circuit before 0 in DC steady state. We solve for the initial condition V in capacitors or I in inductors. After t equals 0, we replace reactors with P impedances and find the differential equation to solve as in a previous video. From the ordinary differential equation, find tau and the final value, and then we write the solution, a voltage or a current. And that is again, my friends. Thank you very much, and I hope to meet with you again in a future video. By the way, I will record this video in the studio at a later date, but for now, this is it.